Here in this video, we would like to talk about the property surface tension. Surface tension is a property of a liquids because of which the surface behaves like a stretched elastic membrane. Let me explain that once again to you. I have done that in the previous video, but I will do it quickly once again for you. You know, if you consider this as a surface of a liquid, because of the surface tension, every molecule on the surface of the liquid experience a maximum downward force on the surface. So they're all pulled downward. But the molecules in contact with the vessel are having an adhesive force of attraction. So they tend to stay back with the surface of that container. Because of that, the liquid, who is supposed to acquire a shape of this much, that means up to from here, it has to acquire this surface, this shape, right? But this surface, free surface, because of the surface tension, gets this kind of a shape. That means simply this upper part is gone. It's not there. So I will just remove it for your convenience. That is not there. So one who is supposed to acquire, the liquid is supposed to acquire this entire shape, has now acquired only this much of the shape. I have explained how it happens based on a molecular theory in the other video. Please refer to the video in the playlist of the surface tension. So what's the area that is being missed is this upper part, this green color, like whatever I'm showing, is missed. So the area of the liquid is supposed to be green and yellow, but the green is gone. Green is no more because of the surface tension property, and it's having only yellow area. Means to say what? It's simply liquids acquires minimum surface area, right? Liquids acquire minimum surface area. This is due to surface tension, right? But you can see it in the real life examples that how does it happen, right? Let me take you a simple example. Let you consider a kind of a circular frame, metal wire with a handle. It's like a bubble blower if you have played in the childhood. It looks like this, right? You generally sink it into a soap solution, get it up. You do see a soap film. You apply a little air over a soap film, bubble comes out of it. You call it like a bubble blower. That kind of a thing, right? So imagine a bubble blower. Imagine a soap liquid film within the bubble blower wire. It's like this. Now let's take a thread, little thread, like this, light weighted thread. Join these two ends together, connect them. You will get a kind of a closed loop. Place this loop gently over here, gently, so that the soap film won't break. Therefore, this is a soap film, and that soap film gently place that thread. So that thread occupies that kind of a zigzag shape here. Now, what's the position? There is a soap film. On the soap film, there is a thread. Soap solution is there everywhere. What I would like to do now is let's puncture the soap solution inside the thread. Where I am puncturing, not everywhere. I am puncturing with a small pin inside. So this is all gone. It's not supposed to happen this way. So I will pour the soap solution once again. Yeah. So I have punctured only in the middle of the thread. Soap solution is there everywhere else, like this. But I have punctured inside the thread here. Here I have punctured it. So it's empty now. I have punctured it. What happens now is there is soap solution outside the thread. Inside the thread, there is no soap solution. What does the soap solution tend to do? This liquids always tries to acquire minimum surface area. To acquire minimum surface area, Every part of the liquid will pull itself this way such that soon you can see a different shape. The diagram, if you draw the same diagram once again, inside you are not going to see this zigzag shaped thread, rather, you are going to see a thread in a circular shape. So, where is the soap solution? Soap solution is in the entire remaining part. So, what happened? Do you notice? The liquid, that is the soap solution, has pulled every part this way so that the thread acquired a kind of a circular shape. Why a circular shape? This is the shape who takes maximum area in two dimensions. As the circle acquired maximum surface, this liquid acquired minimum surface area possible, isn't it? The total area is surface area of the liquid as well as surface area of the thread. Thread acquired a circular shape, therefore it has acquired a maximum surface area. So the liquid acquired a minimum surface area. This is all happening because of a property called surface tension. This is another example that we can say regarding the property of a surface tension because of which liquids acquire a minimum surface area. That's about water drops. That's it. And their shape is the point that I would like to discuss here. Let's take a glass of water and throw it into the air. Big water, you throw it into the air. It becomes small pieces. If you notice that small drops little carefully, each of the drop is having a spherical shape. Observe this drop. You can see these drops are spherical in shape. Why they are acquiring that spherical shape? Why not any of the other shape? The logic is quite simple. That's because of the property of a liquid called surface tension. As it's being said, due to surface tension, water drops try to acquire minimum surface area. So in three dimension, among all the shapes, the minimum surface area is being had by sphere. Sphere surface area is equal to 4 pi r square, where r is the radius of the sphere. Among all the shapes, this sphere is having a minimum surface area. That's why it always acquires a water drop in a spherical shape, not in any of the other shape.